Hello, I'm Jeeya Chavan from the CSC first year A2 batch. As part of our quantum computing assignment, I'll be presenting my topic in this video, which is on Deutsch algorithm. So first, Deutsch's algorithm was proposed by David Deutsch in 1985. This marks one of the earliest attempts to formalize how computation could work on a quantum level rather than a classical one. Next point, it's actually considered the first true quantum algorithm. Even though the task it solves is simple, this was the very first time someone showed that a quantum computer could perform a computation in a fundamentally different and more efficient way. The important milestone, Deutsch's algorithm demonstrated quantum advantage. This means that it could solve a problem using fewer steps than any classical computer could. This was the first real evidence that quantum computing wasn't just theory. It could outperform classical computation. The next key concept is how it works. Deutsch used quantum properties like superposition and interference to evaluate multiple possibilities at once instead of checking them one by one like classical computers do. And finally, Deutsch's algorithm introduced the idea of using an oracle function in a quantum circuit. This approach later became the foundation for many advanced quantum algorithms that we rely on today. Then the question arises, why Deutsch algorithm? So first, let's talk about normal computers. The laptops and phones we use every day, they solve problems step by step. Like if there are multiple possibilities, they check each one individually. One case, then the next, then the next. Basically, slow and steady. Now, here's where quantum computers flex. Instead of checking things one at a time, they can explore many possibilities at the same time. It's like having infinite tabs open, but without the laptop crashing. Deutsch's algorithm is like the first school demo of this power. It gives us a simple example where quantum computing solves a problem faster than classical computing, just because it can explore multiple options simultaneously. And that's the exciting part. Deutsch's algorithm actually proves that quantum computers aren't just different, they can be more efficient, faster answers with fewer steps. That's the dream. So, overall, this algorithm isn't just a random experiment, it's kind of the starting point, the first real sign that quantum computing could become practical, useful, and eventually change how we solve big and complex problems. The party trick. It's one of the most classical examples to demonstrate how Deutsch algorithm works. So, alright, imagine someone holding two coins, each in one hand. We don't know what either coin shows yet. They are hidden, so at this point, both coins should be heads or tails. Everything is uncertain. Now he opens one hand, and boom, it's a head. Now we know the outcome of that coin with certainty. That randomness collapses into a definite result, and here comes the big question. Does knowing the first coin's result give us any clue about the second? Can we magically guess what's inside the closed hand just because we know the first one? So the answer would be classically no, because classical objects have they behave independently. In normal physics, knowing one's coin's result doesn't reveal anything about the other. They are separate, no shortcuts. But in quantum mechanics, things can be different. In the quantum world, particles can be entangled, meaning measuring one instantly gives info about the other, even without checking. So, this is an example of how the first hand and the second hand outcomes are. So, this is head, head, tail, and tail. And according to that, there are all the possible outcomes of the second hand. As we see here, there are only four outcomes, which is head for tail, tail for tail, and tail for tail. So here, the outcomes that are shown are represented in forms of functions. Now, there are mainly two types of functions, that is constant function and balanced function. Moving on to constant functions, it's basically simple. It's like you're having multiple outputs and multiple inputs, but your output is the same. So that we can say that your output is same regardless of your input. So here f of 0 will also be 0 in case 1, and f of 1 will also be 0. In the other case, we can say f of 0 equals to 1 and f of 1 is also equals to 1. So these two are cases of constant functions. Then comes your balanced functions. The balanced function says that your half of the input retains the value 0 and the other half retains the value 1. So in this case we can say that f of 0 equals 0 and f of 1 equals 1. The other case to this would be f of 1 equals f of 0 equals to 1 and f of 1 equals to 0. So this is basically the difference between a constant and a balanced function. Just then comes the circuit. Now the Deutsch algorithm's main content starts. So this is how the circuit looks like. Here we can see that we start with the 0 gate and 1 gate vectors. They pass through Hadamard gates, then through the UF gate, and again through the Hadamard, by which then the main measure is done. Now here, if the measuring is 0, then which means that the function is constant. And if it is 1, it means that the function is balanced. Now let's elaborate how it actually works. So first, we'll just name these states. For example, so this is psi naught gate, this is gate psi 1, this is gate psi 2, this is gate psi 3, this is gate psi 4. So these are the 4 states we have. So by starting with gate psi 1, we'll get here is that. So gate psi 1, we'll see that first we start with 0 gate and 1 gate. Then moving forward, we have Hadamard gate. So the Hadamard gate in matrix form can be written as 1 by root 2, 1, 1, 1, and minus 1. So this is your Hadamard gate. 0 gate can be written as 1, 0, and 1 gate can be written as 0, 1. Then we'll move to the gate psi 1. So gate psi 1, as we see here, is the Hadamard gate operating on gate psi naught. So let's elaborate it further. That is Hadamard gate operating on gate vector 0. So it gives us an output of a superposition state, which is gate 0 plus gate 1 divided by root 2. Then the Hadamard gate operating on gate 1 gives us gate 0 minus gate 1 divided by root 2. So this is your gate psi 1. Then comes your gate psi 2. Now the gate psi 2, if we see here, it's basically when these two are inputted into the UF gate. So before inputting into the UF gate, the two outputs that we get at psi 1 are produced using a tensor product. So we can say that psi 2 is nothing but h into gate 0 tensor product with h into gate 1. So that's 1 by root 2 gate 0 plus gate 1 tensor product with 1 by root 2 gate 0 minus gate 1. So that's 1 by 2. And if we solve this tensor product, the tensor product goes like 0 tensor product with 0, 0 tensor product with minus gate 1, then 1 tensor product with gate 0 and gate 1 tensor product with gate minus 1, minus time minus gate 1. So solving it, we get 1 by 2, so that gate 0 minus gate 0 1 plus gate 1 0 and minus gate 1 1. So this is our psi 2. Moving forward to psi 3. Okay, so psi 3, if we see here, psi 3 is UF gate applied on psi 2. So first of all, we'll see how the UF gate works. So if there are two inputs, that is gate X and gate Y, then the UF gate, when it operates on gate X and gate Y, gives us gate X into gate f of X XORed with Y. So this is basically how the UF gate works. And if we see how the XOR gate works, then we'll just see X, Y, and the output. So the XOR gate only works when both the inputs are unequal. So if you see, or if we put all the inputs here, 0, 1, 1, 0, 1, 1, then the output would be 1, 1, and the rest of them will be 0, because these are equal and only these two are unequal. Then finally moving on to the main procedure, we have here psi 3 equals mu f psi 2, and solving it further, we get its uf into, and as the psi 2, that the value we calculated was 1 by 2 times this product, so that's 1. So solving it further, okay, so first before we do that, we'll just consider this case number 1, and the case number 1, we'll just taking it as a constant function. We are assuming that the function is constant, and we have seen here for different output, then for different inputs, the outputs is the same. So here we know that f of x, that f of 0 is 0 and f of 1 is 1. So when we apply the UF gate, it would be something similar to this. So now solving it further, we get 1 by 2. Okay, so first of all, this is for gate 0, 0. This is for gate 0, 1. This is for gate 1, 0. And this is for gate 1, 1. So as we know from this table over here, we know the values of f of 0 and f of 1. So according to this, we'll calculate the answer. So that's 1 by 2 times. Now, XOR operation, we see that it's gate 0, and we'll put the values of f of x in this equation, that is gate 0 XORed with 0 minus gate 0, 0 XORed with 1 plus gate 1, 0 XORed with 0 minus gate 1, we have 0 XORed with 1. So we know that for XOR, the inputs should be unequal for the output to get 1. So here we'll put the values exactly like this. So this value will be 0, and this case, this value will also be 0. So the answer here will be 1 by 2, gate 0 into gate 0 minus gate 0 into gate 1 plus gate 1 into gate 0 minus gate 1 into gate 1. Solving it further, we get by 2 gate 0 minus gate 1, then we have plus gate 1 gate 0 minus gate 1. Arranging it, we get gate 0 minus gate 1 by root 2 into gate 0 minus gate 1 by root. So we denote this by gate plus, and we denote this by gate minus. So for case 1, we get that psi 4. Okay, so not psi 4, be psi 3. Yes. So for case 1, the value of psi 3 is gate plus into gate minus. So similarly for case 2, case 3 and case 4, psi 3 here will be equal to minus gate plus into gate minus. This would be minus gate and plus gate. Minus of gate minus into gate plus. Okay. So these are the values for psi 3. Now on the other hand, if we see for psi 4, so psi 4 is nothing but we are again using Hadamard, right? So psi 4 equal to H into psi 3, the Hadamard gate operating on psi 3. So if we consider case 1, so it will give us 1 in 1 psi minus and 1 into plus. Because if we see this was earlier gate plus, and gate plus is gate 0 plus gate 1 by root 2. And if we apply Hadamard on it, we'll get gate 0 back again, because H into gate 0 equals to that value. So it reverses. That's how we get the value of psi 4. Now, in the end, Deutsch's algorithm marks the shift towards the true quantum computing. It's our first proof that quantum can outperform classical, not just theory but in action. And honestly, classical computing is logical. But quantum computing, that's where things get exciting. And that wraps it up. Quantum is just getting started. And trust me, the future is going to be crazy. Thanks for staying with me until the end. If your brain hurts, congrats, you understood it.